Hi there, guys. So in the second part of 12F, they talk about phase portraits. And these are a little bit like slope fields, apart from they show you what happens to X and Y over time. So if we have this, for example, this system of linear equations here, and we have a solution to this already, then if you put in an initial point, then you can see what happens to that initial point over time. Okay, so let's show you one of these things. So here's some examples. So if you put in a particular coordinate point, say for example you put in 0, 0, well it may stay at 0, 0, but if you go any slightly to the side of that, you will follow these lines here over time. That's what will happen. And there are many different versions of these phase portraits, but they're essentially determined by the eigenvalues and their eigenvectors. Okay, because of course our solutions that we've got are in terms of eigenvectors and eigenvalues. Okay, so again, let's kind of recap on that. We're talking about putting in a coordinate point and following that according to over time. And depending on the coordinate point you start with, will depend on where you end up in terms of solving for putting in t essentially and solving for x and y. Okay, I think we need to look at an exact example, and then what we need to do is go through all of this here. So there's a ton of information here about what these diagrams are going to look like, and that kind of follows on from the investigation. Now, I'm not going to take the investigation too far. They come up with two examples, and I'm just going to show you how this is working. So I've taken this original one here. I've just made a copy of this, and it says, show the equations of the lines through the origin are in the direction of each of the eigenvectors. Okay, and all they're really talking about there is if you've got 1, 2, and minus 1, 1, they can be changed into these equations here. So those eigenvectors can be changed into these equations through the origins. And you know, if you change 1, 2 into 2, 4, 3, 6, whatever, you're still getting out this equation here. Okay, so this xy depends on two things. It depends on this equation here, and it also depends on this equation here because they're embedded in these eigenvectors. Okay, so for part B, it says choose an initial value for the system that lies on this line here. For example, 2, 2, 4, and find this particular solution to the system of equations. Okay, so let's put that in then. Let's say when we put in 2, 4, it's lying on this line here. Let's put that in here and let's see what we get out. So we're getting out, let's put in 2, 4, and we're saying, well, that's equal to A. Now, that's equal to A e to the minus t, 1, 2, and then plus B e to the 5t of minus 1, 1. Okay, so we've just chosen a starting position somewhere on our xy coordinate grid. And in particular, we've chosen a starting position which lies on the line of this eigenvector. So this is an eigenvector which lies on the line of y equals 2x. We've chosen that. Now, if we turn these into two equations here, we're obviously going to get 2 equals a e to the minus t plus b e to the 5t. And that's not a plus, is it? That's a minus. Sorry, minus b e to the 5t. And then the second line gives us 4 equals 2a e to the minus t, and then plus, in this case, b e to the 5t. Okay, now if we add those two equations together, you can see when we add those two things, you're going to get 6 equals 3a e to the minus t. Okay, so that's a lots of e to the minus t, and 2a lots of e to the minus t gives us 3a e to the minus t. So that's just adding the two equations together there. And so we can see now that we're getting out here, we're getting out sort of half, not a half, sorry, 2, and that's equals to a. I'm just going to write this in a different form here. It's divided by e to the t, because that's the same as this. And then we can say that that's a is equal to 2e to the t. Okay, so there's a. And if we want to work out what b is, well, let's substitute a back into here. So let's choose the first of those two equations. There's 1 and there's 2. So let's substitute a back into the first of those, and we've got 2 equals 2 e to the t, e to the minus t, minus b, e to the 5t. This and this cancels each other out. Take the 2 to the other side. So essentially this is 1. Take the 2 to the other side, and it will give us 0 equals, we can times both sides by minus 1 as well, it will give us b e to the 5t. And since this is never equal to 0, you know, e to the 5t exponential functions look like this. They don't ever hit the x-axis. So that means that b must be equal to 0. So we're getting out b is equal to 0 here. And the point of doing that is to say that it doesn't matter which coordinate point we start with if it's along this line y equals 2x, along the line of the eigenvector essentially. It doesn't matter which coordinate point we choose along this line. We choose 2, 4, we could have chosen 3, 6, we could have done it in a generalized version, we could have chosen k and 2k there. It still would have given us the same answer, that b is equal to 0. In other words, this will disappear. In other words, if we choose a point which is on this line, we'll get, it doesn't matter what time we have here, what value of t we have, we'll always get out some a value, which is giving us, which is taking us further along this vector here. So this is the vector movement. I've chosen 2, 4, could have chosen 3, 6. You could have chosen k, 2k. And so that the value here, if we've chosen it to be along this line, will mean that this is not useful. In fact, it's going to take us off the line. Perhaps you can even see that this is not going to take us in the direction of the line. So to get to 4, it's going to give us some solution which is not based on this. Essentially what that means is that whatever coordinate point we're taking, which is along this line, it will just take us some amount further along this line based on the time and based on this constant a. So in other words, if we're along here, so y equals 2x, we choose a point here, we'll end up somewhere further along the line when at a later point in time. That's what it's saying. We can't go off that line if we've chosen a point on that line. And you can well imagine that if we did this again by choosing a point which is on this line, so on the line which the other eigenvector is on, then this will disappear. In which case, in the line here, let's go, that's minus 1, 1. So let's think minus 1 and 1 takes us to this point, but we can go any amount up there according to that vector. This is this line. This is the line y minus x. If we choose a point along here, again, whatever point we choose, we're going to end somewhere else, end up somewhere else along that line. So we're going to go either this way or this way or this way or this way. I don't know which way we're going to go. We're going to go somewhere else on that line. Okay, so importantly, if you start on one of the lines, you move to somewhere else on the lines. Now that just leaves us with what happens in between. If we choose a point here, where's that going to go? Now, I'm not going to go through the rest of this investigation to come up with examples to find out what is happening. That's going to take a long time, and it's just going to lead to the same results, and the results are the things which you essentially need to learn. So there are a table of results, which I'll try to tabulate, in fact, to find out where things are going. And the investigation, they say, well, look, what's happening when you choose these different points? Where are you going? Where are you ending up? Although the investigation is nice, it's just giving you these central points here. Now, what I'm going to try and do now is go through these points here, and I'm going to go through those with question 2. So I'm going to try and match them to these diagrams here and their equations here as well. Again, it's all dependent on the eigenvalues, and you're going to see where the eigenvectors are too. Okay, and so we'll deal with all of those definitions. Right, and then after that, I'll come up with, at the end, I'll come up with a sort of set of notes for you. But that set of notes is not going to be complete because it's actually really difficult to talk about which things are tending, where the point is tending towards, whether or not it will tend towards the first or the second line, and that's kind of challenging to do. So I'll deal with that through the question. Okay, so I've just copied this one up into here. Sorry, this is a bit small. Hopefully you've got your copy of your book with you as well, so you can see these things, but I will talk through this at the same time. You can see this thing here. So this is all of the important information that you need. If you want to print screen this and print it out, that's a really good idea as well. So it says an equilibrium point or equilibrium solution is a point at which your movement over time in the x direction and your movement over time in the y direction, that's dx dt and that's dy dt, is both equal to 0. There are points which you can take which will lead you back to the same position. Now, an equilibrium point is classed as stable or unstable. If all points close to the equilibrium point will move towards the equilibrium point, it is stable. Otherwise, it is unstable. Okay. So if we have a look in these diagrams here, we can see that if we choose this point here, now you would need to see this through the diagrams, but this one is essentially a point where we have an unstable equilibrium point. So if we chose 0, 0 there, we'd get the solution not dependent on t would also give us 0, 0 through the process which I just went through before, okay, with that particular example. So if we have the solution rather than 2, 4, if we choose the solution 0, 0, in this case, we will end up with 0, 0, and that is an equilibrium point, no problem. But as soon as you move away from that point, you will go in different directions. Okay, so if you move somewhere on this line, it will just take you down this line. But if you move slightly away from the line, it will take you this way. It will not take you inwards. And the fact that it is going outwards means that it is unstable. So this is an unstable example of an equilibrium point in the center. Even though when you put 0, 0 in, you get out 0, 0 again, that tells us that it is an equilibrium point. If we just move slightly further away from that, then over time, this point will move much further away. It won't move back to the center. Now, it does say that all points close to an equilibrium point will move towards the equilibrium point. So if we have a look at, say, for example, this one here, you can see in this case, there's a kind of equilibrium point here as well. But in this case, some points move towards, but some points move away. So this is unstable. In fact, this is unstable and it's also called a saddle point. It's called a saddle point because because sometimes you go towards and sometimes you go away. Actually, I'm not quite sure how that relates to a saddle in terms of horse riding, but you can maybe think of that yourself. And then some of these here, which are talking about if you're moving away. So here we go. This is unstable. So this is unstable. It's unstable, but sometimes you're moving towards and sometimes you're moving away. But this one is unstable, but always moving away. Doesn't matter where you move to around here. To solve the equation that comes from that, you would then move further away over time. So that's called a source. Things emanate from the source. Okay, it's not going back towards. Okay, so this one is a source. This one is a saddle point. This one is also a saddle point because sometimes you move towards and sometimes you move away. Okay, so this is also a saddle point. Now, with this final one here, so this is now your example of a stable diagram. So it's stable because we're always going towards the point of equilibrium being there again. Okay, so this one is the only one which is stable. Okay, now the other ones, unstable is this one, and this one, but the only stable one in this case is this one here. Okay, now the source is this version, and the saddle point, sorry, change color again. Let's change to this color. The saddle point is this one and this one here. Okay, so there we go. We've come up with a lot of the definitions there already, but now we need to think about what influences the fact that we have an unstable or a stable equilibrium point, or a saddle point or a source point. Okay, so now we need to look at this. So this bit here, it's saying when the matrix, I think actually this bit is just standard, right? It says when the matrix representing a coupled system of linear first order differential equations, first order because we're not dealing with any higher powers of x or y than just one, and has two distinct real eigenvalues. The lines for the origin in the direction of the eigenvalues of the matrix give the gradients for the long-term behavior. Okay, actually, that's fairly simple to come up with. So this is pretty straightforward. So this is kind of talking about, take this one for example. So this eigenvector and this eigenvector give us the gradients that we require. So this one is going along the line of y equals minus x. So potentially this one here, or potentially this one here. And this one is going through the line of, with the gradient of 2/3. Okay, that's y over x. 2/3 looks like this one here to me. Okay, so this one I can already see is this one here. So this C, I know I put these out of order here. That's just copied this one across from this side. But C actually matches with C here. The other ones don't match with their own letter. But capital C matches with lowercase c. So I know that because I can see this line and I can see this line here. So I've got those two things. Right, and so basically what it's saying, as t tends to infinity or negative infinity, we end up, long-term behavior of the system ends up going along those lines, either towards the point, towards the center, or away from the center, but long-term behavior ends up going towards those lines. Now what that's talking about is this. We're talking about going towards those lines here or towards those lines here. Okay, so it's going in those directions. That's all it's talking about. Okay, so those lines are defined by these things here, and we tend towards them in the diagrams. Okay, so this is where it gets a little trickier, because now it's talking about the eigenvalues here. So it says when both eigenvalues are positive, all trajectories, so movements essentially, away from the origin as t increases and towards, I've not read that right. When both eigenvalues are positive, all trajectories move away from the origin as t increases and towards the direction of the eigenvector associated with the larger eigenvalue. Okay, so there's quite a lot to unpack there. It says this is an unstable point, so we're talking about two positive eigenvalues. So let's have a look at which one that is here. So that's this one, that's D. The eigenvalue is 4 and 5. So we've also got, this is one of our directions, so we can easily see which one this is going to be because that's 1, 1. It's got to be this one here. And 3 minus 2 gives us the gradient of minus 2 over 3, which is this one here. So that's fine. So I know that D goes with A, and I know we've got two positive eigenvalues there. And so it says that we move away from the origin. So we can see we're moving away from the origin. This is a source. Okay, so wherever we start, which is not at the origin, our equilibrium point, then we are moving away from the origin. So it's unstable. But also there's an important bit of information here, which is really hard to put in a table. It says the points move in the direction of the eigenvector associated with the larger eigenvalue. Right, so what's the larger eigenvalue? It's 5t. The eigenvector is 1, 1. So it's not about the larger gradient here. It's the larger eigenvalue. And the 1, 1 means to say that we are going in this direction over time. So what does that mean? That means that over time, all of these tend towards this direction here. All of these start moving towards this direction here. It is not going like this. So it's not moving in this direction, in the direction of this. It's moving in the direction associated with the larger eigenvalue. Okay, so that's really tricky. That's really tricky in this. And obviously you can identify these without doing that. But that's a really niche little point as to how to draw these diagrams. Okay, so let's have a look at the one underneath. So it says if both of the eigenvalues are negative. So which one is that? So both of the eigenvalues being negative is this one here. That's part B. We can see that that's 1, 3. That's here, the gradient of 3, and 1 minus 1. So it's this one here. So B associates with B here. Okay, now this one says that all trajectories move towards the origin as t increases. So we're moving towards the origin here. So if we're moving towards the origin, then in fact, I think I was wrong in talking about this being a saddle point. Perhaps I didn't talk about it being a saddle point. That one is your stable equilibrium. I think I said that earlier on. This one is stable. This one is stable. Hopefully I said that right earlier on. So, so this is stable. So 2 negative eigenvalues means that we have this stable point, and yeah, this is the only one which is stable, and we don't need to talk about it being a saddle point or a source. That's only when we've got movement going away from the origin. So this is stable in this case. And then it says, and towards the direction vector of the eigenvalue associated with the more negative eigenvalue. Which is the more negative eigenvalue here? We've got the 3t. So things are going to be moving in this direction over the long term. So this direction is this way. And you can see here, in the long term, we are going in this direction here. We are moving out in terms of this direction in the long term. Okay, we are not moving in this direction in the long term. So kind of like the way in which these lines part. Okay, so that again is pretty niche, that point. That's pretty tricky. Now, finally, it says if one is positive and one is negative, we have a saddle point. So that's the final two. So that's this thing here. We've got this one and this one. Obviously, that's this and this thing here. So just clear everything out at the moment. So this is positive and negative, and we're dealing with this one and this one. Now, those two ones are going to be this A and this B. Again, it's quite easy to see which is which. The associates with. But I've got that one right. So those were two negatives. Sorry, so it was C, wasn't it? C associates with this, and A associates with B. Okay, and it says as t increases, all trajectories not on the lines through the origin parallel to the eigenvectors move towards the direction of the eigenvector associated with the positive eigenvalue. Okay, so associated with the positive eigenvalue, so 3, 2, this one. So 3, 2 is this one here. So everything is moving in. Now it looks like things are looks like things are moving in this direction, but they're not. They are moving in this direction. So in the long term, everything is going to end up moving in this direction here. So you've got to follow the arrow direction there. So we're going in this direction in the long term. And we're going there because that's associated. Okay, so moves towards the direction of the eigenvalue associated with the positive eigenvalues. The positive eigenvalue was 3, 2 there. Now, the positive eigenvalue here is 1, 0. What's 1, 0? That's talking about the x-axis. So in terms of the x-axis, where are we moving towards over time? Okay, one eigenvalue is positive, the other is negative, then the origin is a saddle point, so it's definitely this one here. And as t increases, all trajectories not on the lines. So again, on the lines, you might potentially go towards the point instead, but not on the lines. All trajectories not on the lines through the origin parallel to the eigenvectors move towards the direction of the eigenvector associated with the positive eigenvalue. Associated with the positive eigenvalue is 3, is here, sorry, 1 and 0, and 1 and 0 is in the direction of the x-axis. No, I don't agree with that one. I wonder if they've got those mixed up. Hi there guys, just coming back to this one. At the bottom here, this was in conflict with the fact that we matched up this part B here to part A, because it said that when one eigenvalue is positive and the other is negative, then as t increases, all trajectories not on lines through the origin parallel to the eigenvectors move towards the direction of the eigenvector associated with the positive eigenvalue. Well, the positive eigenvalue here is 1, 0. So moving in that direction would mean we will be moving this way over time. And you can see, in fact, that if you choose a point here, it's suggesting that you're coming closer over time. So I wanted to check that one out. And so I came up with an example for this, and I came up with just a simple example here. I said, well, let A and B both equal to 1. And if I choose a point, if I chose the point, for example, 0, 1, to equal this thing here, so to equal this thing here, then the only way of getting that out wouldn't be through this. It would be doing b e to the minus t times by this. Now, b being 1 would lead us to the equation 1. So the y value would be equal to b e to the minus t. Of course, b being 1 leads us to b e to the minus t. Now, to get an answer of 1, that implies that t is equal to 0. Now, I chose another point, and I thought, let's be clever about this, because I can see e here. I'm going to choose the point 0, e. So what am I choosing? I'm choosing 0, 1. So I'm choosing this point here. And I'm choosing 0, e. So that's further up the line here. Okay. So again, you can set that equal to this whole thing. And again, we're going to get 1, sorry, e, or e to the 1, if you like, is equal to, let's set it back, e is equal to, and we're going to set that equal to this part here. And we can say, well, that's, again, if b is equal to 1, we've got e to the minus t coming out there. And you can easily see there that b has got to be equal to minus 1 to get e to the 1. T is equal to minus 1. And that would mean that in this diagram, let's just make those 2 points. So that would mean to say that on that diagram that as time goes forwards, we would not be going up the line. In fact, we're showing that time has now gone backwards, meaning to say we should be coming towards the line instead. So that's showing that those arrows are the wrong way around in that diagram, and that this statement does hold true. Okay, so that when we have a plus and a minus, a positive and a negative eigenvalue, then we're going to move towards the direction of the eigenvector associated with the positive eigenvalue. So we should be moving towards this direction here. So we're moving in the wrong direction. And I've just shown that with a little example there. Okay, now finally, so diagram wrong, we're going in this direction instead. So finally, I did say that I would give you a little table at the end as well. So let's just take a little bit here. And I was just trying to think, how would I come up with this? Say, well, look, here's your two eigenvalues, lambda1 and lambda2. And we've got positive and positive, negative and negative, and positive and negative. Now, when you're positive and positive, your two lines, wherever they are, we don't know that they both have positive gradients, that's for sure, is going to be unstable, and this is going to be source. Okay, if you've got a negative and negative, then it's going to be stable. So we're going to be coming towards our point of equilibrium. So this is our stable case. And then if we've got a positive and negative eigenvalue, then we have this saddle. So we have one of them coming in and one of them going out. Now, the direction that you're going to get depends on the positive one. So we're going to go towards the positive eigenvector. Now, I don't know which one that is in this case, okay, but whichever one is associated with the positive eigenvalue, whichever vector is associated with the positive eigenvalue, that's the thing which you're going to go towards. And my diagram is obviously there. Okay, but that's not to say that this is a positive gradient. Could have been the other way round. Okay, we don't know. So the eigenvector is not necessarily going to give us a positive gradient just because we have an eigenvalue which is positive. So in this case, we would get a graph which would look like this. Okay. So the tricky bit is with this, I'm sorry, I didn't write, this is a saddle and this is unstable. And this is also unstable. Okay, so unstable equilibrium points. Now, yeah, the tricky bit with this is just to draw the rest of the diagram. If we're positive and positive, then we need to go in the direction of the eigenvector, which is associated with the larger of the two ones here. And the one which has the largest magnitude here, the largest negative one, is the direction of the diagram as well for all of the other points. So that's why it's kind of difficult here to put all of that information into a table, because it's not clear which one of these is going to be associated with the largest negative eigenvalue here. Okay, so that's kind of a partial table which might be useful for your notes, but again, you need the full notes in order to start thinking about what's the full direction of the diagram. Okay guys, well thanks for listening to that one, and good luck with the exercise.